Good morning or afternoon, ladies and gentlemen. Today we will be covering problem 43 of chapter 16, which asks for the net electric field at point X due to a charged tube of length L and total charge Q. Theoretically, we could look at this problem as a collection of point charges that make up the cylinder and add up their contributions using the equation E equals 1 over 4 pi epsilon naught Q over R squared. But that would be rather difficult, and I have no idea how to do that. So I'm going to do things a bit easier and look at this question as the sum of contributions due to a bunch of charged rings along the x-axis. And these charged rings, when stacked up on top of each other or integrated, form our tube. Now we know that the electric field due to a charged ring is 1 over 4 pi epsilon naught dq, or qz, over r squared plus c squared to the 3/2. And proof of this can be seen in section 16.4. It's out of scope for this video, but it's using another integration to prove that. It's a good resource. The first thing that we have to do in this problem is determine our linear charge density along the x-axis, which is Q, or the total charge of the tube, divided by L, or the length of the tube, and that allows us to find the charge behind any given point on the x-axis. Using this, we can conclude that dq equals lambda dx, or at any arbitrary point x along the x-axis, our charge is x lambda, or q over L. So dq is q over L dx. We also determine that z, or our distance between some arbitrary point in our cylinder and point x, is simply w minus x, where w is the distance between the origin and x. We substitute our two variables, z and dq, into our dE equation to form 1 over 4 pi epsilon naught q over L times w minus z over r squared plus w minus x squared to the 3/2 dx. And we integrate this to get the total, the summation of the contributions of these rings along the x-axis. What's important to note is that we are integrating from 0 to L because the rings start at 0 and end at L, or the length of the cylinder. So we substitute our dE equation for d ring, and we use a standard table of integrals to land this answer. We substitute for our limits of integration, 0 and L, for x, and we get this 1 over 4 pi epsilon naught q over L times the difference between our two limits and our non-constant part of the equation up here. Thanks for watching. Good luck.